Thank you again for the opportunity to speak at this workshop. I'm absolutely stunned that once again I'm the only person talking about FPGAs. You'll be able to judge at the end of the talk why that might be. This is a presentation of work under the EuroX project, and it's by two of the partners, University of Manchester, where I am located, and the Hartley Centre at the STFC Daresbury laboratory, where I used to be. Last year I gave a talk about the matrix vector kernel, so I'll give an update on that work. And then the second half is this interesting aspect of whether we can make the task a little bit easier by using OpenCL as a route into the FPGAs. This is an outline of the EuroX project. It's the same slide I showed last year, so I'll skip it. You can read the stuff in the slides online. And I'll also skip this. This is a basic introduction to the Elfric weather and climate model, which is being developed at the Met Office. I will just point out the important thing which will come later, which is that Elfric is built using Cyclone, which is a domain-specific language or a domain-specific compilation system, and that will become important later in that it uses the separation of concerns concept, where you separate the science code from the stuff you need to run on a parallel architecture. What is our motivation for using FPGAs? The FPGA is a chip which has on it a lot of logic blocks connected via interconnects that you can program on the fly, so that you can essentially design any piece of logic that you want using this device. So that flexibility is a big advantage, but it can also be seen as a disadvantage. So on CPUs and GPUs, the design of the chip has already been done for you, and it's had the hell optimized out of it by the likes of Intel and NVIDIA, and works pretty much optimally under a whole wide range of situations. With an FPGA, you have to do that yourself. The big potential gains are in performance per watt and in performance per dollar or per unit cost compared to CPUs and GPUs. Another great potential advantage is in consideration of reduced precision. On a CPU, you generally only have two options for floating point format. On an FPGA, you can design an adder or a multiplier to operate with any format you like. Totally flexible. In a similar way to the way that high-performance computing is able to leverage on a mass market for GPUs, we can also do the same with FPGAs. They've been used for many years in the embedded computing sector, and they're now being used widely in data centers for cloud services, for data analytics, transaction processing, business-to-business computing, that kind of thing. They're being used there because of their benefits in power efficiency and in cost. So we in the high-performance community can leverage on that. The hardware's traditionally been led by Xilinx and Altera. Altera were bought up a while ago by Intel, so Xilinx and Intel are the main hardware components. And in both cases, you can get a single chip, a multiprocessor system on a chip, MPSoC, which has a MultiCore CPU and an FPGA on the same chip. I went into some detail last year about the process by which you can take a C kernel and generate code for the FPGA. I've now distilled that down into 3 steps. There are always 3 steps to heaven, aren't there? So you take your C kernel and you pass it through what they call high-level synthesis. Programming FPGAs has usually in the past been quite a low-level activity with engineers programming directly in VHDL and Verilog. But these days you can take a piece of C code and the Vivado HLS tool will compile that into an IP block. So that's like compiling a module for a CPU. There you end up with an object file. Here we end up with what they call an IP block. And the second stage is to lay out your design on the FPGA chip using your blocks and blocks from a library that Xilinx provide. And that's very like the link process that you're familiar with, and you end up with an executable thing that's called a bit stream. And that bit stream is loaded onto the FPGA and maps out those programmable interconnects between the logic blocks. You also need a driver on the CPU, just as you would if you're using a GPU as an accelerator. You need to be able to drive that accelerator. Same thing with the FPGA. So here are 3 slides on those 3 steps. This is Vivado HLS. It produces an estimate of the performance, the latency in clock cycles. So over here on the left, in this top left block, you can see 2,334 cycles, which is the amount of time it predicts this matrix vector kernel is going to take. It produces also a timeline, so you can look at how the instructions have been laid out in time. And I've checked here that I'm getting multiplies and adds issued in the same clock cycle, so I'm getting the kind of pipelining performance that I expect. I should say when I first put the code in, it took 69,000 cycles, and there are a number of optimizations that I had to go through to bring it down to this 2,000 figure, which represents 1.65 flops per cycle, which is approaching the ideal of 2 flops per cycle, a multiply add every cycle. As well as the performance, the other thing you're interested in on an FPGA is how much space it's taking on the chip. And this bottom right-hand box tells you how many of the basic blocks it's using. These things called BRAM, DSP, these flip-flops and lookup tables, these are the basic logic blocks that exist on the chip. Whoops. And this tells you how many of them you're using and the number that are available. So for this small kernel, we're only using a few % of the chip. But the idea is we can replicate this kernel. So I now have a design. This is the second phase, the, as it were, link phase. Each of these blocks in the middle with this little HLS logo, each one of these is one of my matrix vector blocks. There are 12 of them. I'm intending to run 12 in parallel, so I get parallelism by replicating the block across the FPGA. That's a little like multi-threading. The rest of the blocks you see there are from the Xilinx library. There's one called Zinc Ultrascale, which is your interface to the ARM CPU. So there are where's my pointer gone? There are 2 ports here, which are where the data come from the CPU. These things with crossbar kind of symbols in the middle are crossbars, and they're used to connect things up. That's a protocol converter. And then there are 12 blocks here which are BRAM, block random access memory, which is like a fast cache. It's memory, but it's still on the FPGA. And I've got 12 of those, so I've got a block of memory for each matrix vector block. And the ARM code then has to drive this. Each block has some registers, called registers. They're really locations in memory with bits that allow you to start and stop the block and check whether it's active or not. So on the ARM code, you can set the AP start bit and watch the AP idle block bit to see whether when it's finished, and when it's finished, you can copy the output data. And there's some mucking about here with addresses. The BRAMs that I mentioned are mapped into user space on the ARM, and you write and read memory, write and read data to and from the BRAM on the FPGA by writing and reading from those memory locations. I originally did all this coding in C because I thought I had to, but I then realized that actually you can maintain the Elfric spirit. Elfric is written entirely in Fortran, and when I did the Elfric, when I implemented this stuff in Elfric, I was able to do it all in Fortran using the ISO-C interface to interface with things like the map system call that you need. So I can see most programmers would throw their hands up in horror and say this is far too low level for me. I don't want to be bothered about data paths here and addresses and setting and interrogating bits and that kind of thing. But there are some ways out of this low-level approach. The beauty of Cyclone, as I've briefly explained, is that it does separate out the science code from the parallel gubbins, and our intention is that in the future Cyclone will generate the FPGA code for you, which is great. Programming models are developing all the time. The introduction of this high-level synthesis technique is just one of those, and it's now possible to use OpenCL code with as a starting point for FPGAs. So with this work on the matrix vector kernel, we've been demonstrating capability using the low-level tools, and then our intention is that we can map that onto a higher-level interface for the main work. Here's some performance. So across the bottom here, you can see the number of matrix vector blocks. I said there were 12 in the design. I can run with any number from 1 to 12, so that shows you the scaling with the parallelism on chip. The other parameter you can change is the clock speed. So you can have any clock speed you want, really. You can just set the clock speed. So I've got 3 different examples here: 100, 250, 330, 3 megahertz. I think the maximum for the hardware is around the 600 or 700 megahertz for this particular chip. This is quite an old generation chip. And you can see there the scaling with whoops, there it comes, the scaling with clock speed. So we have a parallel efficiency across these 12 blocks of 87% and an efficiency on the clock speed scaling of 94%. There are 3 factors which you can isolate which determine the performance that you're getting. I should have said the headline figure here is 5.3 gigaflops, double precision. 3 critical factors here: the performance of an individual block, how many blocks we can fit onto the FPGA, that's an obvious factor, and the clock speed. This little block here is the clock wizard, which is how you generate different clocks. So those are the 3 important factors. With the performance of the single block, I think we're doing quite well. As I said, we're approaching the two flops per cycle. That is the aim. The problem with increasing the number of blocks and the clock speed is that eventually you run into timing constraints. When you do this linking phase to generate a bit stream, Vivado has to check all the data paths and check that the timing is right for signals propagating across the chip from one block to another. And if the timing doesn't work because the clock speed's too fast or because the complexity of the network is too great, then it will fail to generate the bit stream. Here's a performance comparison with an Intel multi-core CPU, a Broadwell with 8 cores. Using all 8 cores with OpenMP gives you 9.86 gigaflops. We're getting 5.3 gigaflops. So we're in the same ballpark. But as I said at the beginning, you have to bear in mind these chips are much less power hungry, maybe a factor of 10 less power, and they're also cheaper. I'm not sure about the exact figure there, maybe a factor of 2 or 3 in cost. So the fact that we're in the same ballpark is great. Some more comments on this. There's a white paper from a digital signal processing company called Burton, where they do a GPU versus FPGA performance comparison, and they give figures for the euros per gigaflop per second per watt, which is the relevant metric there, and the gigaflops per watt is the relevant metric for power efficiency. It's also worth saying, you'll see a lot of work in the literature about people implementing matrix multiply on FPGAs. Matrix vector is much harder. There's a much lower computational intensity in the matrix vector kernel. Both these issues are discussed in much more detail in a paper that we've just produced that I've cited at the bottom, which is in press in Scientific Programming. That's full of a lot of detail. So having got this matrix vector kernel running, the next step was to take the Elfric code and actually implement parts of that on the FPGA. So I now have Elfric running on the ARM CPU, and I have taken 2 kernels. One is called apply variable HX code, which is part of the Helmholtz solver, and one is a pure matrix vector multiply, like I did in the simple example. And by making slight modifications to the Elfric code, I can offload those onto the FPGA. There are 2 ways of doing this. You can either simply intercept the single cell kernel. In Elfric, they refer to cells, which are the individual cells in the horizontal mesh. That is actually a column of data. So they're referred to as cells, but you can think of them as columns. And the Elfric kernels operate on a single cell, a single column, within a loop. So you can either offload just a call to a single cell, but it's much more efficient, obviously, you get more parallelism if you can offload a loop, a kernel which operates over multiple cells. So that's what I've also done by making a multi-cell version of the kernel. That means playing around with the Cyclone generated code. But this is an obvious optimization for many architectures, and I think that will come in Cyclone. So what I've done is to offload these 2 kernels, apply variable HX code and matrix vector code. They appear one after the other in the code, separated only by a halo exchange. So that gives us now the opportunity to see how it's going to work on the FPGA with halo exchange. And that's these to be done red lines, where we want to keep the data on the FPGA and only exchange halo data with the CPU. If we're doing MPI on the CPU, another option which is being explored in the project is MPI between FPGAs, an analog of what you already do on GPUs with GPU Direct. Not much time left to go into the OpenCL side of things. Clearly, there are benefits of using OpenCL because it already has execution and memory features which map well onto accelerators, onto GPUs, onto FPGAs. So we're exploring that. You can run the code already through these products from Xilinx called SDSoC and SDXL. What is Cyclone doing in this space? Well, Cyclone now generates an independent representation as its middle form. So originally, you would just have Fortran code running through a Fortran backend and generating Fortran code. But with this intermediate representation, you can now generate other things, and the guys at Hartree, particularly Sergi, has used the Nemo Lite 2D as an example. This is a cut-down version of Nemo, which just does a 2D, just does the two-dimensional part of the ocean. But it does contain 11 kernels and 300 lines of code, which is quite big as an example to run on an FPGA. This gives an example of the intermediate representation. So on the left here, you can see things like a subtract operator and an I and a 1, and that corresponds to I minus 1 that you see over here. This is the intermediate representation generated from the Fortran code, and this is the OpenCL that it is generated from the intermediate representation. They've run this code on a different type of FPGA to the one I was using. This is an Intel FPGA connected with PCI Express to an Intel MultiCore CPU. And you can see some preliminary results in scaling with problem sizes, weak scaling. So flat is good. There's some slight improvement in efficiency on the FPGA as the problem size grows. This is comparing with a single core of a KNL. Clearly, it's not giving stellar performance, but this is initial result before any optimization. Lots more things going on in Cyclone to close that performance gap, blocking functional parallelism and fusing kernels. And the idea also is that we take the experience of doing all the low level stuff to help optimize the Cyclone generation. So in summary, we have a matrix vector kernel implemented using Vivado HLS on the UltraScale Plus FPGA. That's the Xilinx product, producing 5.3 double precision gigaflops. And the Elfric weather climate code is running on this system with 2 kernels offloaded onto the FPGA. We're looking at using a high-level OpenCL programming model as an alternative, and the Cyclone team are now generating OpenCL code in the hope that when we bring all this together, we've got a route for porting Elfric onto FPGAs. Thank you.
Great, let's thank the speaker.